If you stand in an old church and look at the floor, you might notice a violet and teal shadow cast through stained glass. It is a highly structured, vibrant projection that seems to contradict everything we believe about the dark. We usually define a shadow as a void, a simple black patch where light failed to reach. It is an absence, an empty space. Yet during a total lunar eclipse, when the Earth stands directly between the moon and the sun, the moon doesn't vanish into blackness. This image shows the result. It glows with a deep copper red, a color provided by light bent into the darkness by Earth's atmosphere. These moments show us that a shadow is a physical record. It is the universe refusing one path for light and creatively redistributing the remainder into a new structure. When linear light strikes a barrier, the central waves stop. Their forward trajectory is denied, but waves wrap around obstructions.
The surviving frequencies fill the gap with alternate colors, creating a structured gradient in the dark. This is the signature of a shadow, the physical result of what a system does with energy that was expected but denied. We see this principle at work on a massive scale 13 billion years ago. This dense field of galaxies was captured by the James Webb Space Telescope, showing highly structured systems existing shortly after the Big Bang. Standard models of gravity suggest these massive systems formed too quickly. There simply hasn't been enough time for matter to naturally clump together into these complex shapes. If gravity alone didn't have time to pull these together, we have to look for a hidden force that pushed them into existence. This push came from the regions where light was most heavily obstructed, from the cosmic shadows cast by the universe's first blockages. To model this, we look at Exorelis, or space resistance. Imagine the early universe as a transparent ocean of light flowing through space until it hits massive, jagged, dark clouds of primordial gas. These clouds acted like dams. They completely blocked the flow of light, casting shadows across the fabric of space itself. When flow is blocked, pressure builds, creating a resistance well. This slow-moving eddy traps energy and compresses space. Here, matter found the resistance needed to cool and clump rapidly, igniting the first stars and spinning into structured spiral galaxies. Structure was forced into existence by the pressure of these cosmic shadows. The first galaxies were born because the universe found a way to bridge the gap created by refusal. This same logic applies to the way we process information. The universe presents us with a continuous stream of data, but it also presents us with interruptions. We can measure this as the shadow expectation gap. It is the mathematical difference between the signal a system expects to see and what actually arrives at the sensor. You experience this gap when your eye ignores its own blind spot, or when your brain maintains the trajectory of a car as it passes behind a pillar and temporarily disappears. When the expected stream of reality is cut off, an intelligent system does not crash. It responds to the shadow. This response is called shadow coherence completion. This brain scan shows the biological hardware responsible for bridging those gaps, calculating the missing data to maintain a coherent picture of the world. Artificial intelligence uses this same process. When a neural network reconstructs a missing corner of a photograph, it isn't seeing the pixels. It is predicting them based on the shadow left behind by the missing information. Processing visible light is a simple reaction, but the ability to maintain coherence when light is withheld is the functional definition of intelligence. It is the act of filling a gap responsibly, rather than collapsing into the dark. From the birth of galaxies to the reconstructions of a neural network, the goal remains the same. When the signal fails to arrive, an intelligent system uses the shadow to complete the picture.